All right, let's look at some more limits with a graph. So the limit as x approaches 1, so we're going to come in and trace in on the left side. And what y value does it look like you're getting closer and closer to? Well, it looks like you're getting closer and closer to 2. And if you come in from the right, what y value does it look like you're going to run into as you get closer to x equals 1? Well, it looks like you're getting closer to 1. So your left limit and your right limit did not agree. You're coming in and you're approaching two different values. So when that happens, if they're disconnected, like they don't actually look like they would meet together, or they don't approach the same value, then the limit does not exist. And there's a famous movie by Miss Lindsay Lohan where she exclaims in the middle of a math competition, the limit does not exist. That's what she was really talking about. There were two values that the function was approaching. It cannot decide what to do or which one to approach, so it can't exist. So for part G, if you traced in on the left side, what does it look like it's doing as it gets closer to x equals 0? Well, it's just shooting down and down and down and down. So it's shooting down to negative infinity. And then this side on the right, as it gets closer to x equals 0, it keeps shooting up towards positive infinity. So did they approach the same value or same thing? No, they're different. So the limit does not exist. So that brings us to some cases of D and E, or where it does not exist. So we've looked at one of them with two examples. So that's when they had differing values. They do not approach the same thing. The second one is when you have unbounded behavior. So like 1 over x squared, its graph looks like this. It does not exist since the function increases or sometimes decreases if it went down without bound. It does not approach a real value or an actual number. So in order for the limit to exist, it has to approach like a number, not infinities or something. And then the third one is when it oscillates. So like sine of 1 over x, this is the graph. And the reason why it looks pretty solid black in here is because it's actually bouncing and down so close together that you can't really distinguish individual curves. So it's bouncing in between 1 and -1. So since it's bouncing incredibly fast, it can't decide which of the two to actually land on. So it does not exist. So it's alternating between -1 and 1. So these are your three cases of D and E. This one doesn't happen too often. Every once in a while it has to kind of be a specialized function. This happens quite a bit, and this one is pretty common too. Not as much as that one though. All right, let's look at some more graphs and then that'll do it. So these you're gonna have to graph on your own. Oh no, you gotta remember how to graph stuff. Yep. Okay, so the limit of f of x is x approaches 1, and our function is ln of x. So ln of x looks like that. It's got a vertical asymptote at 0, and it hits the x-axis at 1. So as you trace in from either side, oops, be consistent with my colors, you're going to trace in, and as you get closer and closer to x equals 1, what y value does it look like the two sides would connect at? 0. So the limit as x approaches 1 of f of x is 0. Okay, moving on to part B. Uh-oh, you've got a piecewise function. Oh gosh. Well, have no fear, a mathematician is here. So g of x is equal to x squared if x is less than or equal to 0. So this is a parabola, and normally it would go like that, but we can only keep the part that's less than or equal to 0, so just the left side. Okay, the second part, or second piece, is 2x. That's just a line, but we can only keep what's greater than 0. So anything over on the right. So nothing down here, just that. So as you approach x equals 0 from both sides, looks like they would both run into 0. The answer is not always 0, by the way. Just it was for these. All right, part C. Oh gosh, now we have a trig function. Oh dear. So it's sine of x when x is less than or equal to 0. So you only want the graph that's on this side of it. So sine is normally that wave. It does hit 0, 0. And if you drew it this way, it's going to go up. So if you draw it on the other side, it's going to go down. Second piece is x squared. You only want for x is greater than 0, so anything on this side. So keep that right side of the parabola, not the left. You already drew stuff over here. So as x approaches 0 from both sides, it looks like you're going to run into, dun dun dun, y equals 0 again. Okay, one more and then that'll do it for this section. Oh gosh, now you got an exponential function. That's all right, we've done those before. So e to the x. E to the x normally goes like that. It gets flat on the left and it shoots up on the right. Well, you can only keep stuff that's less than 0 or things that are on the left. So you can only keep this little flat part. And there's no equal bar, so I'm going to leave it open. And it's really at 1. Because if x is 0, I could plug it in and that would be 1, so that's where the hole is. Now, this one, second piece, that's a line going through the origin with a slope of 1, so kind of like that. And it's got the equal bar, so I'm going to make it a closed circle. Now the reason why I differentiated here and did not differentiate for the other ones is because like on this graph, they connect together as well as this one. And if an open circle and a closed circle connect, the closed circle wins and it fills in the open. If they're separated, then you gotta distinguish which one's open and which one is closed. So anyway, so as you approach x equals 0 and you trace, it doesn't look like they're going to connect together. The left side is approaching 1, the right side is approaching 0. So if they approach different values, the limit does not exist. Okay, so go ahead and try the homework out, the worksheets, and let me know if you have any questions whatsoever. And have fun with these.